Hello again, physics friends. Today we're going to be focusing on the gamma factor. As you remember, we've seen the gamma factor already in time dilation. So if you recall time dilation, we had the following. The time elapsed on a clock at rest is a factor of gamma larger than the time ticked off on a moving clock. Okay, so that's where the gamma comes from. Our goal today is just to get a sense for what values gamma takes as a function of speed or velocity. Okay, so we're going to end up making a plot. And on the x-axis of this plot will be v, and v is going to go from 0 up to the speed of light, acknowledging that a massive object can never travel at the speed of light, but it can get arbitrarily close to the speed of light. And the y-axis will be values of gamma. Well, the first thing to notice is, let's look at a few values of gamma. What if v was 0? Okay, well, if v is 0, then we have gamma is 1 over the square root of 1 minus 0, so gamma is just 1. So on the left side of our plot, we're down at 1 when x equals 0, when the speed is 0, excuse me. So we can put a dot there. And let's just pick a few kind of representative values, okay? What about if v is equal to 3/5 of the speed of light? So that's 60% of the speed of light. And we can play the calculation game again. Gamma equals 1 over the square root of 1 minus v over c squared, right? So v over c is equal to 3/5. V over c squared is equal to 3 squared is 9, 5 squared is 25. So we have 1 over the square root of 1 minus 9/25. Well, that is 1 over the square root of 25ths, excuse me, which is the square root of 25 over 16, which is 5/4. Okay. So when let's see, if we break this graph up into 5 chunks, 1/5 c, 2/5 c, 3/5 c, 4/5 c. So here we have 3/5 c, and we have a gamma value of 1.25, or 5/4. Okay, so here we go. We put a point on our graph right there. Okay, let's pick a couple more. If v equals 4/5 c, okay, and in that case, v over c squared is 16/25, which actually is similarities to the previous example, but it's a little bit different. 1 minus 16/25 in that denominator is 1 over 9/25 in the square root, which is square root 25 over 9, which is 5/3. So 5/3 is roughly 1.6, 1.7. So we'll put that right here, 5/3. And that's for a speed of 4/5 c. So we put our dot right there. So this gamma factor ends up looking something like this, where as the speed approaches the speed of light, gamma approaches infinity. Just to be clear on that, if v equals c, gamma is 1 over the square root of 1 minus 1, so that's 1 over 0, that's infinite. So we don't consider the actual speed v equals c, and we'll get into that. We'll get into the reason why in a little bit. But so what we would say is as v approaches c, gamma approaches infinity. Just as an example, if the velocity is 0.999 c, right, then you can calculate what gamma is, and you'll find that gamma is 22. So if we look at our scale here, we have 1, 1 1/4, 1 2/3, and then as we get to 0.999 c, we're up at 22, which on this graph is off the page. So you can see this is a very rapidly rising function as v approaches c, but it's actually fairly flat, even all the way up to 4/5 c, or half the speed of light, 3/5 c, 4/5 c. We're still below 2 for the gamma factor. But as we get very close to the speed of light, gamma gets arbitrarily large as v gets arbitrarily close to the speed of light. Okay, so just to summarize and reflect a little bit, some key takeaway points from gamma is that gamma is always bigger than 1. Okay, gamma is always bigger than 1 for v bigger than 0, and gamma equals 1 when v is equal to 0. Okay, and so whenever we multiply by gamma, we are increasing a value. So what we can see in this time dilation equation is that the left-hand side is going to be bigger than delta t clock moving, and it's bigger by this factor of gamma, which is larger than 1. The other takeaway point is that as v approaches c, gamma approaches infinity. Okay, and let's just look, for example, at this v equals 0.999 c, gamma is 22. And if we take that gamma and we look back at the time dilation equation, okay, what this is saying is that for every 1 tick of the moving clock, the clock at rest ticks 22 times. So it's not at all a small effect, it's an enormous effect. That say Alice's clock on the rocket ticks 1 time, tick up and down, and in the meantime, Bob's clock is ticking 22 times, up and down, up and down, up and down. So when we say there's no such thing as universal time, this is exactly what we're getting at. That these 2 clocks, Bob's and Alice's, are ticking at different rates by a factor of gamma, and that factor of gamma can be very large indeed. All right, that's it for now. We'll see you again next time.